Hi class, so welcome to part 2 of the AC motor control demo. And in this one we're going to be showing just a little bit of similar stuff, but I wanted to kind of point out a couple things that could be helpful for your projects, as well as some things that would be helpful in application. So first, I'm going to demonstrate using this motor. I got a link here in the documents, but here's the motor on Amazon. What's interesting about this motor is I just sometimes see students that want to do a project where they want to have something, a motor to run something, but not necessarily have to get a battery pack or a power adapter to do a DC motor. And there's a variety of AC motors out there that you could use. They're pretty cheap and simple to use. This is an example of a synchronous motor. How this motor works is almost exactly the same as the stepper motors from our class. And I have a picture here, a screenshot from there's a video that I'll put in the playlist. But inside these motors, the construction is almost exactly the same as our stepper motors, where you can see there's these alternating teeth patterns. Where in a stepper motor, you would power one coil and then another coil, and then get the permanent magnet rotor to rotate to a position. Well, in a stepper motor, you turn on and off different coils at different times. In this synchronous AC motor, it's still a permanent magnet rotor, except for the stepping is done just because it has an AC waveform. And so it's pretty simple to get these motors to rotate. So construction-wise, they just have two coils, and each coil has two wires. So there's 4 wires coming out of the motor. And to get them to work, you can see in this diagram here, there's 4 wires, 2 yellows that should be connected together, and then one of the coils will have, so one coil has a yellow and red, and the other coil has a yellow and green. And the intent is you connect the yellows together, and then now you choose to power the the red or the green directly, and then the other one is powered through a capacitor. And remember, the capacitor gives a phase shift, so that way that second coil will be 90 degrees about apart from the phase of the first coil. So now those 2 coils will be seeing their peak voltages at different times, and therefore act like a stepper motor. So it's still an AC motor, so you can plug it into the wall and power it without needing a voltage adapter or batteries or anything. So the motor comes with like a capacitor like this, and again, if you want to go one direction, then you connect to the red line, and then the main is on the yellows, of course, but you choose the red line, and then the green gets its power through the capacitor. And if you want to reverse it, connect directly to the green line, and then the red will get the phase shift through the capacitor and spin the other direction. So very similar to the motor that we demonstrated in part 1, except for now just smaller and probably more project size for this class. And you can see here there's a variety of 110 volts, so you can plug them in the walls, and then you can choose your RPM. They're just geared differently to get different speeds, which will also have different torques. Right, the smaller the RPM, more likely have a much larger torque. So this is a 6 to 10 watt, and if we choose, let's say the 1 RPM. Maybe that'll update. That says 10 RPM right there, so maybe this is a typo, but you can see still about 6 to 10 watts. So a slower speed, but you probably end up having a higher torque. Oh, no, the picture's not changing at all. Maybe that's just the default picture, I guess. Anyway, so pretty simple. The motor also comes with a shaft that's got a flat side to it, so you can mount easily, or a through hole so you can connect things to it. There's you can see here it's kind of meant for barbecue, like rotisserie motors. So, but again, there's other varieties of motors like this. You can get the synchronous AC motors that are pretty useful for projects. Again, now the trick is do you want it running continuously, or do you want it turning on and off? Or if you want it to reverse directions, all of that we can do and control with our relay. So to demonstrate how to do that with our relay, You see here we have the two yellow wires connected together going to the motor, and then we have either the red or green connected by the capacitor, and those are connected to each of the individual relays on our relay module. And then we connect AC power. So one of, like, let's say the neutral wire is connected to the yellow wires, and then the hot or the black wire can be connected to both the comms on our relay modules. So now all we have to do is connect using the Arduino to control. Do we connect power to the green first? And then if the green is connected and we don't connect this one, the power to go to the green, power that coil, and then through the capacitor, power the red. And then it'll spin one direction. Or we can not connect this one and instead connect this guy. Don't do both, but connect this relay. And then now power will go through the red coil first and then through a phase shift through the green. So we can control the direction. Or we can turn the motor off just by turning both relays off and the motor will stop. So you see here we connect our relay, ground and 5 volts, and then our pins 2 and 3 are connected to the relay. So the code for this is pretty simple. You have the 2 pins, so counterclockwise pin is pin 2, clockwise is pin 3. And then we set them as outputs. Again, the relays are off when they're high, so we set them both high to turn them off. And then if we want to go clockwise, we set the clockwise pin low to turn that relay on, and it can turn clockwise for 3 seconds. And then we set the pins high to turn them off for 1 second. And then we turn the counterclockwise pin low for 3 seconds to get it to spin in the counterclockwise direction, and then we turn them off by making them both high. So it should turn clockwise for 3, off, then counterclockwise for 3, and then off, and then just repeat. So pretty simple. So let's actually demonstrate that. So I'm going to make this full screen here. So I got this connected. Because again, here's the motor, 30 revolutions per minute, and we got our red and green wires are connected to the capacitor and then to the relay. And so the red is connected into the normally open on the top relay, and the green, I ran out of green wire, so it's a black wire going to the normally open on the bottom relay. And then we connect, I connected neutral, the white wire, to these yellow wires, so they're both powered with the neutral connection. Ground's not being used, and then the hot on our AC line is connected and then split to the COM of both. Okay, now remember, this is wired with AC, so I don't want to rub the bottom of this, short anything out, shock myself a little bit, or set this on anything metal that could short it out. So anyway, reminder, just be careful when you plug stuff into AC. You don't short it out or shock yourself with it. Okay, now what we're going to do is, this is already programmed, so now I just got to plug it into power. I'm trying to get the wires to sit still here. Plug it into power, and it should, again, turn clockwise first and then counterclockwise. So there's clockwise for 3 seconds, counterclockwise for 3, and it just repeats. And you can see the relay module is telling you which relay is being powered by which light is being turned on. There you go, pretty simple. So again, a pretty simple motor that you can purchase for projects. They're pretty strong. I mean, I can't get it to stop rotating just by holding it. So it's a lot stronger than the motors that come in the kit, that's for sure. So, a couple notes about this is again, the direction being controlled is by which coil is being powered first, just like the other motor in part 1. And then the speed of this motor is governed by the frequency of the AC waveform. And if you wanted to change the speed of this motor, you would have to change the frequency of the power going in. So if you really wanted to do that, you would have to get a variable frequency drive, or just pick a different motor that's designed to run at a different speed. And you can do that from Amazon or other sources. But it's I thought a good demonstration of there's more motors out there than just induction motors. This is not an induction AC motor. It's basically a stepper motor, but powered with AC power. And so it's called a synchronous motor because it doesn't have slip. It will spin in sync with the rotating magnetic field created by the AC waveform. Okay. So let's see, we demonstrated that. Just want to make sure we covered everything. Oh, and there's a video here that's linked that shows how these motors are made. It's pretty interesting. I'll just put it in the playlist for today's videos in the YouTube channel. So again, 2 phases produce, one phase has a capacitor to shift the AC power, so that's how it creates the second phase. Yeah, I think we covered those pretty well. Okay. A note here, I'm not going to demonstrate this, but another way to wire this is I could just use one relay where power is going into here, and then it's either going to this coil or that coil. And this is fine. It's just this motor will never turn off. It'll always, because this is the normally closed, it'll always either spin clockwise or counterclockwise. You can never turn it off. You have to somehow interrupt power here. So you could maybe run this through this and then have this relay be the on and off, and then this one the direction. That's just a different way to power it. Maybe that's better than this one here, but well, if you want to try that, go ahead. Okay, other topics I want to talk about. Different ways to control the speed of AC motors. So just want to explain a couple things here and not necessarily demo them, but so here's some different ways you can control speed of an AC motor. Okay, we've talked about controlling direction by controlling which phase is being powered first. So now we're going to talk about speed. So one way you can adjust speed, use a gearbox or pulleys. Right, gear it down or gear it up to change its speed. This is common, but it's not a good way to vary the speed on the fly because it's constructed that way. Another way you can change speed of AC motors is purchase one that has a different number of poles. For example, this link here, which isn't really a link, I should change that to be a link. It can be, it can change from a 4-pole to a 6-pole motor. And so what that does is if we change our poles and our synchronous speed, or our synchronous speed calculations, you can see with a 4-pole, it should have a synchronous speed of 1800 RPM, but with a 6-pole, it should have 1200 RPM. Here's an example online that does that. There's this link here where you can purchase a motor that has different speeds. I just downloaded this spec sheet here. And on the spec sheet, you can see that, again, it has different power ranges and different speeds. So here's the 2 speeds. Remember, 4-pole synchronous speed is 1800 RPM, so this is meant to run at 1725, so a small percent slip. Or a 6-pole, it will have a synchronous speed of 1200 RPM, and so this will run at 1140, so again, a small percent slip. So yeah, this is an induction motor, but again, you can wire it differently to get different speeds. As shown down here. Here's the 4 or 6 poles in the diagram. There's also, this document shows you the dimensions, and what I wanted to show here is the wiring diagram. And so you have, on the outside, you'd have 3 screw connections that you could wire to, and then internally, here's the wire on the wiring internally. But externally, you'd connect to the 3 screws. It says here if you want high speed, connect to the high and COM. So you'd connect your power to high screw and the COM screw. Or if you want low speed, connect to low and COM. So you can, again, connect your power to low and then COM. And then, again, that's one way you can get variable speeds. So it's not very practical because you'd have to rewire the motor. But again, that's another option. Another way that you can change the speed is by changing the voltage. However, this only works on some motors. If it's an induction motor, this will not work. It's not a good idea to change the voltage of an induction motor. But there are other types of motors. For example, the synchronous motor that I just showed. If we were able to reduce the voltage, that would likely reduce the speed by cutting down the power, its ability to get to that speed. A better case is on universal motors. And universal motors, remember, are basically AC, DC motors, or they're DC motors that are field wound that act just like DC motors when powered with AC, because you're switching the magnetic field and the current through the coils at the same time. Put a couple links here to some examples that would do that. Let me open that up here. There's just too many pages open. Okay, here we go. So there's a variable speed controller for, again, a couple different types of motors, but again, it needs to be basically a universal motor. So like this would work for your blender or other types of motors in your house that are basically DC motors that can work on AC. And so all it does is it really just cuts out power. It reduces the voltage. Here's another one, a little more basic, but again, it's a speed controller because it's just cutting out the AC voltage. And so those will work in those cases. But if you have an induction motor, then this won't work. Oh, and another problem is most of them have a knob that you have to turn to control it, so it's not something you can do with the Arduino. And you can't control the direction of rotation. It'll just change the speed. Okay, if you do have an induction motor, then really the best way to control the speed is through a variable frequency drive. And cover that more in class. But again, a variable frequency drive is changing here we go up to this. If we're changing this equation, we're not changing the number of poles, we're changing the frequency f, which changes the synchronous speed, which will change the operating speed of the motor. So again, this won't work if it's a field wound motor. So if it's like a universal motor, changing the frequency doesn't matter. It'll still spin in the same direction and same speed. If you want to get a VFD, here's a link to Amazon. It's just saying search for variable frequency drive. And you can see here, if I just search for variable frequency drive, there's a variety of options. I probably wouldn't buy a VFD off Amazon, but it's just an easy place to show you a lot of options. So here's one you can see. It's got single phase input, but again, it needs to be single phase 240. So this would take like if this was in your house, then it would take both quote phases, because they're really in phase, right? So it'd be a single phase 240 volt input, kind of like what your oven or your electric dryer would run off of. And then it could output a 3-phase output to power a 3-phase motor. Here's a 3-phase input variable frequency drive. Oh, sorry, no, single phase input, again a 3-phase output variable frequency drive. Let's see. Anyway, there's just a variety of types. They're not super expensive, but again, the idea is you're able to control the frequency now, which can change the speed. Now, a lot of these you have to control manually. There's a knob or buttons or something that you can adjust the speed. There's others you can buy that you can connect through to a computer or be controlled through maybe even an Arduino, where now you can have a program on your computer or your Arduino that's changing the speed of the motor. So most of the ones here are shown, they're again meant to be more manual. So you just want to demonstrate this. If you really want to change the speed of an AC motor and it's an induction motor, then you just need to buy a variable frequency drive. Okay. All right, so that concludes what I wanted to show for part 2. Thank you.